Welcome back to the deep dive. So, if you're building with generative AI today, you already know the game has it's fundamentally changed. We've moved past that proof of concept phase, and we are squarely in enterprise production now.
Right.
And the challenge is no longer just, using an LLM. It's about understanding this really sophisticated, multi-layered stack you need to engineer one robustly.
That's absolutely right. And this deep dive, well, it's your roadmap. We've pulled together sources that cover the entire LLM engineering lifecycle. It's a shortcut to expertise, really.
But what are we covering?
We're unpacking 3 critical layers. First, the foundational physics of how these models actually read and learn.
Okay.
Then the production stack that makes them trustworthy, which is our RAG. And finally, the professional skills and, the validation you need for real-world deployment.
Okay, let's unpack this. Starting with the literal engine under the hood, the core architecture. So the big technical breakthrough that let us leap from those older, sequential models like RNNs. It was the transformer architecture.
It was.
And its killer feature wasn't just speed, it was the ability to do true parallel processing through the attention mechanism.
And that shift right there from sequential to parallel, that's the whole strategic insight. Older models, they had to read a sentence word by word.
And they'd forget the beginning.
Exactly. By the time they got to the end, they often lost the context. Attention just changes everything. It lets a token instantly weigh the relevance of every other token in the sequence, all at once.
So it solves that long-range dependency problem.
Completely. It was notorious for a reason.
Give us a concrete example. So if I say, the cat sat on the mat, which was black, why does attention matter there?
Well, because without attention, when the model hits the word black, it has a problem. Does black refer to the mat or to the cat?
Right.
So self-attention lets the system instantaneously compare the focus token, that's the query, black in this case, against all the other tokens, the keys. It assigns a really high weight to cat, and that confirms the dependency.
And that's what those 3 vectors are doing, query, key, and value.
That's their core function. The attention score is just the math, the dot product, that tells the model where to focus.
But if you're processing everything in parallel, you make them over. You lose the sequence, the order of the text. So how does the model know that Alan walks dog is different from dog walks Alan?
That's where positional encoding comes in.
Yeah.
It's a brilliant solution. Since attention itself has no idea about order, this technique injects information about the position of each word right into the embeddings.
How does it do that?
It often uses some pretty complicated math sine and cosine waves, specifically to create a unique signature for every single position in the sequence. So the final token embedding has both the meaning and its position baked in. It's critical.
Okay, so let's move from the architecture to efficiency. Because building these models it's massively compute intensive.
Oh, yeah.
Full fine-tuning is still prohibitively expensive for most, which is why PEFT, or parameter efficient fine-tuning, has become the standard.
It really democratized model specialization. PFT methods like LoRA low-rank adaptation and QLoRA, they just slashed the computational demands. They made this kind of adaptation feasible for almost any serious engineer.
Okay, so explain LoRA. How does it cut VRAM requirements so much without actually shrinking the deployed model? That feels a bit counterintuitive.
It's ingenious, really.
Yeah.
LoRA keeps the original huge foundational model weights completely frozen, doesn't touch them at all.
Okay.
Instead, it introduces these tiny low-rank adapter matrices right next to the frozen weights. And during training, you only update these small new matrices.
And because they're so small.
The training cost just plummets. Then when you deploy, you just merge those tiny matrices back into the frozen weight. So the final parameter count, the model size you serve, doesn't increase at all.
Now here's where it gets really interesting for anyone working in the enterprise. QLoRA. That takes things to a whole other level.
Yeah, the true insight of QLoRA isn't just saving memory. It's that it took this ability to fine-tune massive models, something once only for hyperscalers, and put it in reach of a regular enterprise engineer.
No. It combines LoRA with 4-bit quantization.
It does.
But quantization means using lower precision, which that usually introduces error, right? How does it maintain performance?
Think of it like a super efficient digital photo album. You store the huge album in a heavily compressed format. That's your 4-bit quantization to save space.
Okay.
But when you want to actually edit a photo, you pull it out in high resolution, say 16-bit precision, to make sure your edits are accurate. QLoRA does exactly that. The bulk of the model is stored in low precision, but the crucial computations happen in 16-bit format.
So the important stuff, the learning part, is protected from the compression.
Precisely. The higher precision LoRa adapters compensate for the storage savings.
And that's the aha moment. I mean, the sources mentioned the practical impact of this was fine-tuning a 65 billion parameter model on a single 48 GB GPU. That is staggering. All right, so an efficient specialized model is one piece of the puzzle. But when you put it in production, you immediately hit two huge flaws.
You do.
One, the model fabricates things. And two, its knowledge is instantly out of date for your internal data, which is why RAG, Retrieval-Augmented Generation, is an absolute necessity.
RAG is the architecture that provides the guardrails. It's the live knowledge stream. It augments the LLM with fresh, trusted data from your internal knowledge bases, from your enterprise systems, and it forces the model to ground its response in fact.
I think the stock trader analogy is still the best way to explain this to a non-technical stakeholder.
It's perfect. The foundational LLM, that's the trader's static historical data. It's vast, but it's old.
Right.
The RAG system is a live market feed, the internal analyst reports, the specific client histories. RAG turns your static business data into intelligent, context-aware prompts.
And successful ag all comes down to smart data prep. The main hurdle is still chunking.
Oh, it's a brutal trade-off.
You split documents into pieces small enough to search, but then they're too small to provide meaningful context.
It is the single biggest headache for ag engineers, and it drives all the innovation. Simple RAG either sacrifices precision with big chunks or context with small chunks.
So what's the advanced solution?
The one gaining the most traction is the parent document retriever.
Okay, how did that get around the trade-off?
It uses a dual retrieval process. So it uses small child chunks just for the first step, the precise vector search.
Right.
Once it finds the right small chunk, the system then retrieves its corresponding much larger parent chunk and feeds that full document segment to the LLM for the final answer.
Ah, so you get the best of both worlds. Precise search, rich context.
Exactly. It's a solution that exists only because engineers spent a year wrestling with that problem in production.
Now, that's for unstructured data. What about graph RAG? When does building a whole knowledge graph become worth the effort over just simple vector RAG?
That's a crucial question. A knowledge graph is a massive investment. Vector RAG is great for semantic search on, huge piles of documents. But if your application needs to understand relationships,
Like who reports to whom, or which part goes into which product?
precisely who bought what dependency chains.
Mm-hmm.
If those connections are what matter, graph RAG is essential. It retrieves based on structured links, not just semantic similarity.
Let's talk quality. How do you evaluate a RAG system when the output is creative and, variable? Traditional AI metrics don't work.
No, they're useless here. What's fascinating is that GenAI evaluation needs entirely new frameworks. We're now focused on metrics like relevance, factual accuracy, or groundedness, consistency, and fluency.
Which means you need human feedback.
It means you have to implement things like user-centered feedback loops, rating systems, annotation workflows. But crucially, we're also seeing the rise of LLM as a judge systems.
So you use one LLM to score another one's output.
Yeah. It lets us iterate on quality so much faster than waiting for slow human ground truth every single time.
Okay, we've covered the mechanics, the application layer. What does this all look like when we move it to actual cloud deployment?
Well, the big strategic decision really comes down to speed versus control. You've got two main paths: a managed service, like a model as a service API, or a custom deployment.
The DIY route.
A DIY route, exactly. Managed services are incredibly fast for testing and MVPs. But the GPU-backed endpoints can cost, 3 to 5 times more than a custom CPU endpoint.
So the classic trade-off, deployment speed and convenience versus total cost and control.
That's it. Custom deployments using containers or VMs, they give the highest control and the best cost efficiency for production scale, but your time to deploy just goes way up.
And then there's compliance.
On top of all that, enterprise deployment demands strict adherence to security and compliance. We're talking SES2, IGPay, GDPR.
How does the Argon architecture actually help engineers meet those demands?
Well, our RAG is actually critical for auditability. Since the LLM is blocked from directly accessing any sensitive data, the RAG system is the controlled gateway.
Okay.
It enforces strict access controls. But more importantly, RAG provides a clear audit trail. Because the system provides citations, the sources it used, developers can prove the output is grounded only in verified, approved internal data. That's a huge deal for compliance.
That link between RAG and auditability is a key takeaway. So, last thing. If an engineer masters this whole stack from attention to RAG to the cloud, how do they prove it professionally?
Certification is the standardized benchmark, specifically something like the AWS Certified Generative AI Developer Professional. It validates that an engineer can move past a prototype and build a real, secure, cost-efficient solution.
And the weighting of that exam actually confirms everything we've talked about today.
It absolutely does. The largest domains are foundation, model integration, and implementation. It confirms that mastering fine-tuning with PEFT and LoRA and building resilient RAG systems, these aren't optional. They're the core competencies.
We've really traversed the full roadmap then, from the core math of the transformer through efficient specialization with QLoRA to the architectural necessity of RAG, and finally, validating that skill set.
And if we connect this all to the bigger picture, the entire process of building a trustworthy LLM relies on what we call alignment.
Making sure the model's output aligns with human values and rules.
Exactly. And that requires advanced optimization techniques that go way beyond just simple fine-tuning.
The sources mention two major approaches here, PPO and DPO. What's the strategic difference you need to know?
PPO, or proximal policy optimization, is an on-policy method. So think of it as learning through continuous real-time trial and error. It's like practicing chess and getting live feedback on every single move.
Which sounds computationally massive.
It is. DPO, direct preference optimization, is an offline method. It learns from a static, curated data set of human and agentic examples. The preferred answers are already provided. It's much cheaper and more stable. So for your continued learning, the next deep dive question is this: can a model truly achieve robust, safe mastery by only passively reading the right answers, which is the DPO approach? Or is that continuous, messy, real-time practice of PPO essential to turn a model's ability to evaluate into truly reliable generative performance? That's the next major challenge for AI alignment.
Until next time, keep digging.